Right, so we have roughly 3 sections here. We start with a look at covariance in an empirical data set, just as it's done in the materials, and we give a few comments that are maybe not there in the materials, so you will gain something by following us. We do a generation of surrogate data, which is extremely important to know how to do it carefully and with proper settings. And we finally introduce the idea of principal component analysis because it's such a widely used thing that comes under many disguises, but we talk about the basic concepts that you need to understand whenever you apply such a thing to large data sets of your own. If we have a few minutes time, we can answer questions. Otherwise, we have something prepared to show you how that might go into the future, and we'll be finished about 5 o'clock. Right, so our covariance matrix will look at a famous data set that deals with the number of furs that were gathered in a company in Canada in the 19th century, where the Canadian lynx is known to prey on the snow hare. And these data are thought to represent one of the oldest examples of correlated data in a natural environment where some fluctuations are thought to be non-random. We then look how to compare this against a null hypothesis that these data are actually generated by random processes, so non-deterministic but random processes, and for this purpose we need multivariate data, and we'll introduce you to the relevant function within MATLAB. And we'll finally look at how to deal with higher dimensional data sets, how to find strongest covariances among many hundreds or potentially many thousands of data sets that you might have gathered, and how to go towards forming clusters or defining clusters within such data sets. Okay, that's enough said for this context, and I think I'll start by talking a little bit about the Hudson-Bay data, and Rob might join me and do some things in MATLAB. Maybe if you open your MATLAB script that you have prepared. So the first thing that we want to do is to have a look at how to calculate the covariance when we have more than a single data set present, and we do this on the Hudson-Bay data set. 19th century recording is around 100 years of recording have led to co-varying or at the same time recording the count of lynx furs and the count of hare furs, which were delivered to that station in the Hudson Bay. And we get this data set. You can either download it from our webpage, or Rob will have it here on our desktop. So maybe you start by opening this data set.
Okay, let's make sure it opens in MATLAB. Just open it as it is.
Oh, just load it. Yeah, that's what the data set looked like. So you can see if you open it with a text editor, it's just numbers. So it's an ASCII file, just contains the pure numbers in 3 columns. One column contains the time. So that's the year when the count was taken. Second column contains the hare count, and the third one is the lynx count.
Okay.
So what we want to do, we first need to have this data set into MATLAB. We can do this with, what function will you use, Rob?
I'm going to use the load function. And so MATLAB will know to look on the desktop.
Take the video away, because then you can concentrate on our MATLAB. So the file called Hudson-Bay data.
Will this need quotes around it, or it should be fine? Should we try? Okay, so it seems to have loaded it in. We have this new Hudson-Bay data in our workspace, so we know that worked. And we can see there's 43 rows and 3 columns, as we saw in our original data.
Okay.
It'd be useful if we can put this into vectors, so that we can more easily refer to this later. So of course the first vector we're going to call hare. and we know that that's the second column. So every row in the second column. And similarly, we want the links data, and that's the third column. Okay. It's always good to plot these things. I think you'll agree, Gerald?
Yeah, we might just have a look at it.
So let's start a new figure, and simple plot just with the links and the hair data. Okay, so if I run this script, then our plot pops up. So the blue line is the links in this case, because that was the first thing I passed to the plot command.
Okay, then if you pass that first, so that's the third column. Yes, the links is the smaller number of furs, so we can see the hair is the larger number of furs.
How do I get the...
So blue is the links data and green is the hair data.
So if I insert a legend, okay. So that's good, but that's not really fulfilling what we wanted to do.
Okay, now what we want to have, we have two time series, and we suspect that there's an interaction between them because we know the links prey on the hairs. So we suspect that there might be covariance between these two data sets, which is also visually suggested by this going up and going down in some probably regular fashion. But we want to have this quantitatively. So now we try to use this formula that is already in the script and try to implement it. And how can we calculate the correlation between these two data sets?
Okay, so the first thing I want to do is I'm gonna make sure these are in comments, because I don't want the plot coming up every time I run the script. But if I put them in comments, then we can refer to them later if we want to. It's always good to comment on what we're doing. So I'm going to say calculating covariance. Okay, so we can't directly convert this equation into MATLAB script, because we're actually doing a loop over the hairs and over the linkses. So we're going to have to do this a bit differently. Well, first of all, we need to know this n. So what's this n? It's the number of samples in the system. So the first thing we do is n equals length. Yeah. We could do length links, because we know there's as many data points for hair as links.
Right.
Now we need to pull in. So we're going to have to sum over all of these values. So we need to start up a sum that we're going to initialize to 0. I think I can't spell, but nice. Sum, and we're going to set that equal to 0, of course, as we've got nothing to start with. Then we're going to have a loop, which we're going to sum over everything. So for we're going to have an I thing in every loop, an I variable in every loop, and from I equals 1 to n, because there are n samples. Now what do? Well, we update our sum. So sum equals, say, 2m's. We can end this as well to start with. So that's our complete loop. So in each loop of this, each time this loop gets processed, we know we at least want the sum we had before. But what do we want? Well, we want this component here. So hair I minus the mean of hair times by links I minus the mean of links. Actually, I think we can just copy this, because I think that's in the right syntax already. Plus, of course. Does that look right to you, Gerald?
Yeah, it looks good. So we have sample point hair I. We subtract the mean of the hair values, and we multiply this difference with the difference between the links data point at corresponding, so the same I, minus the mean of the links data. So that's part of it. Yes, that's all that we have to sum up according to the rule given up there.
So we've done this part of the equation now, so the sum, but we actually need to normalize. And for some reason, the covariance isn't 1 divided by n; it's 1 divided by n minus 1.
Mm-hmm.
That's part of the definition of deriving the covariance for data sets. So we finally want to calculate the covariance. I'm going to call this HB.
Hudson-Bay covariance, yeah.
And that's just the sum divided by n minus 1. And I hope you can see that this code here is exactly equivalent to this equation here. And then I should run this. Oh, we've come up with an error. I've missed out a bracket. Can we see that? Oh, I know. I've done square brackets when I should have done round brackets. Okay. Let's try running this again. One final thing, I'm going to clear my screen and I'm going to remember to put a semicolon at the end of my loop equation. Otherwise, every time I run this loop, it will output the value of sum, and we don't really want that. So we just want the output of the covariance result. I run this. Finally, we get our right answer of about 275.
So we get an answer. The covariance is now quantified. And the thing that we have to remember is that this quantification is not normalized. So the value of the number will then depend on how you put the numbers in. So if you have fur counts, you get this number here that's on the order of some hundreds. But if you have values, say, that are less than 1, then of course also the covariance will be in small numbers. Right, so remember that this covariance is an unnormalized value, unlike correlation. So if we would do the Pearson correlation coefficient, that would be a normalized value, which would be between -1 and +1. This is not the case in the covariance. So we just need to remember that. Okay, so we have seen how we can implement this code. And what we could do is, for example, we could use this segment that you have calculated here. We could put that into a function and call it COV. And then it would, every time you would say COV, it would output the covariance. And this is just what MATLAB does when defining its functions. So we have seen how to actually program it by hand, but we're not going to do it later on because MATLAB provides us with more convenient ways of doing it. But this is the way that you will be getting used to actually implement your own functionality into a piece of code that does what you want to do it. What you want it to do. Right, so let's start a new script. I leave the other one open, then we might come back to it later on. And now look at generating random data. Now, why would that be important? Because we want to test now whether the covariance found in our empirical data are actually valid or significant with respect to some null hypothesis. And one null hypothesis here could be that this data set is produced from random fluctuations. So we want to compare actually, are these data compatible with the hypothesis that this is all random output, so that the fur counts are randomly varying, or that there is actually some mechanism behind it other than just random processes. So for this purpose, we want to find random data. And if we're interested in covariances, we must find a way to generate random multivariate data. Multivariate data. Multivariate data set means more than one data set.
So like we had before, we had for every point in time, we had the links data and the hair data.
Right, there's two sets, so that would be a bivariate data set, but in general multivariate, as many samples as you take. And this is, of course, of importance if you have omics data, where you can take, as we said, a couple of hundred or a couple of thousand measurements for each point, say using microarrays or related techniques. So what we can do here is we define our multivariate data set, and we need to know what MATLAB function that is to do it. It's something called MVN, multivariate normally distributed random data. So random data, mvnrnd is the functionality, and as usual it goes with brackets. So what does this need? We need to input 3 arguments. The first argument is the mean of each of the data sets. So if we just assume we have measurements that come out as mean 0, it would be 0 and 0 if we want to have two data sets as an output. So we have the mean of the first data set 0 and the mean of the second data set is 0. We will then need to input a matrix, which is the covariance matrix, namely to have defined all potential combinations of calculating the covariance as before. And that means if a data set is compared to itself, it's the variance, variance against itself.
Which is the square of the standard deviation.
Squared of the standard deviation, which we can just set arbitrarily to 1. And then the next entry point is the covariance between the first and the second data set. And we can just define it as if there's no covariance, if that's random data that are uncorrelated, it would be 0. And we need to have a 2 by 2 matrix. So in the second line, we have the same value because it's a symmetric matrix. And we have the variance or the squared standard deviation of the second data set. And let's just, for convenience, also put it to 1. So that's a simple 2 by 2 matrix for uncorrelated data sets, two uncorrelated data sets, or two data sets where there's no covariance assumed. And the third argument that we put in, we can specify the number of samples that we want to have. So if I say 50, then we will get 50 data points. That will generate our data sets. And if we now want to have the covariance matrix, to see the covariance matrix of these two data sets, then we can get it easily in MATLAB by using the cov functionality. That's the covariance matrix. And we just need to say over what it is taken. It's taken from the two data sets defined previously as random numbers. So we have two data sets produced from random numbers. They're normally distributed. And we get the covariance matrix by using the cov function. So I make a comment on this. That is get covariance matrix of multivariate data. So what we are doing here, if I execute this, we can look at our window, at our command window, and we can see that we do get a covariance matrix. It's 4 numbers. It's a 2 by 2 matrix. And isn't there a little bit of a surprise, Rob?
Well, they're not the same numbers we put in the first place. We put in 1, 0, 0, 1 as our matrix.
Right. So we had ones along the diagonal, and surprisingly, the upper left figure is 1.59. So that's quite far away from 1. And also the off-diagonal matrix element is quite different from 0.
Yeah. Or at least it's symmetric.
It's symmetric, that's nice, but that's by definition, so it can't be otherwise. So what if we do this whole thing again? If we execute this again, we get another covariance matrix, which looks rather different now. You can see that both the diagonals, the auto-variances or variances are different. They're now 1.18 and 0.83, but the covariance between the two data sets is now negative value. So why is it different?
Well, we're only taking 50 samples, and that's not very many in the scheme of things.
Right. It's too few data, but it's randomly generated data, right? Each time you run this mvnrnd function, it will produce different numbers. So each time we expect a different output. But what we can do to see that this actually works nicely, if rather than 50, we take 500 samples, then we can produce another matrix, and we can see it's getting slightly better now. This last thing, maybe just do it again. Run this again, and we take a look, and we have now values that are much closer to the value of 1 along the variance or squared standard deviation of the two data sets, and they are closer to 0 now in the off-diagonal covariance.
So this is just with small sample numbers, there's a large error effectively in our results.
So we must bear in mind that we get surrogate data sets, but because we have a small number, we get very large fluctuations there. Very large fluctuations, so we can't really say for sure what our exact covariance is. We have a broad distribution of covariances that we get with this way. And this is, of course, relevant also when we try to compare it with the Hudson-Bay data. Now, that was now for uncorrelated data sets. Let me just do one thing before I continue and make this font a little bit bigger, because I can see from my test screen that this is too small. So maybe you can easier read it if I have this font a little bit bigger. So rather than typing it again, we just now modify this script, and where we had previously 0, which meant no covariance, we now put in some covariance value that is larger than 0. And in this case, I just suggest a value of 0.8. And because it's symmetric, it must be put in twice. So that's now a matrix that assumes that between the randomly generated data, there's covariance. There's a covariance between them. They have something in common. They behave similarly, although they are random. And if we do that again, same, we can leave 5,000 samples, so we can actually see whether that's a good value. And the covariance matrix, we can now call that, give that a different name. So I call it, well, this is not, previously was uncorrelated, now it's correlated data set, to just have another name. If we execute this and look at the result, we can see above was the uncorrelated with 0 off diagonal matrix entries, and now we have an entry that's pretty close to 0.8, it's 0.79. So correctly, this matrix reflects this relationship that is between the two data sets. So what has it helped us? It has helped us to produce a data set that has a certain predefined covariance between them. Let's take a look at this data set, what it looks like. I go back to my uncorrelated data set. Call that uncorrelated. Have maybe not so many, just take, say, 100 samples, get 100 samples and look at them. So we can actually, maybe it's easier if we just outsource them and call the first data set is which one? M. Which one is the first data set? All data points of the first column. And the second data set is M. All data sets of the second column. So data 1 is our first data set, and data 2 is our second data set. And we can now plot these data. We plot data 1 and data 2. And if we put that into square brackets like you did before, that will plot both our data sets and all the samples that we have in there. So let's do this and let's see the result. The result is two data sets plotted here. Blue is the first data set, green is the second data set. And we can see, well, not very much. What do we see?
It just looks completely random to me.
It looks like there's no
data.
Obvious correlation between these two. So let's do the same plot with some correlation as we have just done it previously. I fill in my values 0.8 and 0.8 in the off diagonal, assuming correlation, having a correlation between them, and then again doing the same plot. We get an output that now looks somewhat different. We maybe don't look at all the data, just look at the first 20 samples. So here we can see what is meant by covariance or correlation. Can you detect a little bit?
So it does look like when it's high, it's a high number. It's so high. When the first value is high, the second value is also high, and similarly for when the first data point is low, the second data point is also low.
It's not there in all cases. You can see there are deviations, but in some cases it seems to be true. And if we now look at more data, you can see that there's a certain tendency to do same thing. Both go up or both go down and assume similar values. And that is meant by the presence of correlations or, in general, interrelations between these two data sets. So this is important because only when you look at data both data in the same way, you will be able to see these correlations somehow reflected. What can we do? One way of looking at correlations is to do a scatter plot. So let's also do a scatter plot for these two. And let's call data 1 against data 2. And what would you expect? What do correlated data sets look like? I mean, they're doing similar thing.
So roughly, as one thing gets bigger, the other gets bigger as well. So it should look more similar to a straight line, I guess, than just a...
More tending towards a straight line, but along which value? So let's look at it. You can actually see there's something there. Where would be the straight line? It's very hard to see maybe here. So what I'll do, I'll make it a little bit obvious by using 1,000 or even 10,000 and making this plot, and will become more obvious that these are now aligned along the main diagonal of this scatter plot, and this shows us the presence of correlation. We can see this, and we want to compare this against a similar plot showing no correlation. So going back to our zero correlation data set, we have uncorrelated data. And if we do the same plot, maybe we make a new figure this time. The new figure, that's what it would look like if there's no correlations between them. Try to make it a similar setting, and then we can compare the two. Uncorrelated data set have this circular distribution, which means there's no preferential direction. Correlated data set have the preferential direction.
So in the graph on the left, if we know the value of one of the pieces of data, we can't really say anything about the other. Whereas the one on the right, we might want to say that if our first data point is large, then the other variable will also be large, or vice versa.
Yeah. So that's what it means, being aligned along the diagonal. And you can test out for yourself, as is done in the materials. Anti-correlation, negative values for the correlation between them will lead you to something aligned along negative diagonal. So they will be orthogonal to what we see right here. Okay, so that finishes our multivariate data, but we want to conclude this by... we can save this. And we want to conclude this by going back and taking a look at whether we can use this in our previous data set. So the question is now, can we produce multivariate random data that have the same mean value as our Hudson-Bay data set and that have the same covariance as our Hudson-Bay data set? So how would we do this?
Okay.
We need to know the mean values and the covariance.
Yeah. Okay, so we calculated the covariance before, but we need the covariance matrix. So variance matrix HB, and now that's equal to, we're going to use the cov function again. We give it the two variables, hair and links, now in that order. And should we see what happens? Should we see what that matrix looks like? Okay. So
yeah, that looks good.
That's promising. So the covariance across on the diagonal, which will be the hair versus the links, that's actually the same as what we had before. So that's
275 exactly.
Yeah, that's times by 0.2 times by 1,000. So yeah, equal to the same thing. That's good to know that we calculated the right thing before, but obviously this is far easier to do it just using the cov command.
Yeah, and we can see also the variances are now in the order of 1,500 and 390, so they are very large, but that depends, as we said before, on the way the data are entered. Okay, and now with this knowledge, with the knowledge of this covariance matrix, we can now actually define our surrogate data set, so random data that reproduce these features, the
Okay.
mean and the covariance matrix.
So our surrogate data. So we're going to use this multivariate normal random function again.
No A.
Oh, I'm sorry, there's no A. So we need to give this, recall, two pieces of information, first of all. The mean of the hair and the mean of the links.
The mean value, right? Because there's non-zero mean, we need to compare it. And then the second argument was the covariance matrix.
So I'm moving on to another line so we can see it. So we need to give the covariance matrix, which we just calculated.
And finally, third argument, the sample size. I have to remember how many data points were there in the Hudson-Bay data.
We've already calculated that as n.
That was calculated as n, so we know it's 43. Yeah.
Should you see what happens when we run this? Oh, I've finished with the wrong bracket. Okay, so we've generated some data. That looks reasonable, don't you think?
Yeah, except we can see that, of course, because they are normally distributed, they can produce negative values. So that's a functionality of the normally distributed random numbers, and you wouldn't think that you would get many negative values in the Hudson-Bay data set, but that's something that we accept for now. But if we were to do serious research, we would account for this and maybe take them out or somehow correct this so not to have negative values, because there's a clear bias. We don't accept negative values in the natural data.
Yeah, we don't often get negative numbers of hairs or lynxes. I guess we could either just discard the negative values, or we could use a different use a different distribution like the log normal.
Yeah, we can use different distributions. So let's just leave it for the moment. These are surrogates that have, supposedly, we have 43 data samples in the surrogate data as well. And we have a mean that is similar to what we had in the hairs and a mean that is similar to what we had in the lynx, and the covariance between the two should be similar. However, because remember we have a small sample set, the numbers are not necessarily the same. So let's maybe take a look and see how do we get the covariance of just any of the artificially produced surrogate data sets.
Okay. So again, we need to calculate the covariance matrix using the cov function. I'm going to give it now the surrogate data. So we want to know what that looks like. I guess we're only interested in the diagonal elements now. We're only interested in how hair and lynx are.
The off-diagonal.
The off-diagonal, sorry.
The relation between the two. So that's why we only look at element 2.1 or element 1.1,2.
Yeah, because they're identical, because it's symmetric.
They're identical. Okay, so that if you don't put a semicolon there, we'll see it on the command window.
If we run that. Okay, so that's now 255. We had 275 or so before.
Yep. So we get some reasonable value, not the exact same value, but some reasonable value from the data set that we artificially generated. And while we don't go into this, but if you now wanted to work with it, because you have this functionality there as many times as you want, you can create 1,000 such data sets from the random number function generator and then see the whole distribution that you would expect from randomly distributed but co-varying data sets.
Yeah, just to demonstrate that, if we run this again, that's even quite a lot bigger. So even just with these, I think it was 43 samples.
Yeah, because it's only 43 samples, the distribution varies widely, and we can get comparatively much larger and much smaller values as well. So that means we have to be very careful when drawing conclusions. So the fact that the original covariance was 275 is by itself not impressive at all, because we first have to see how randomly generated data sets would distribute, and then we can compare against this and see whether there's actually a covariance that can be explained by non-random correlations between the data sets.
I think it'd just be nice to finally plot this data to see what it actually looks like. So this surrogate data, just to make sure it has kind of had the same sort of look similar to the data we had previously. Okay, so we can see as something goes up, as the number of hairs go up, the number of links go up, and vice versa, roughly.
Yes, because we have artificially introduced some covariance, this is also reflected. So there's a certain degree of covariance now captured in here. And one thing that we don't get is the periodicity of it, because we haven't looked at Fourier spectral components. We've only looked at the covariance. So this is the feature that you then get. Right? So this will be a way of working with such surrogate data. There's much more to be said, but we can leave it here as this. Anything you can define your feature that you are interested in, get it from the original data, and then produce your null hypothesis data that allow you to then to say whether or not this null hypothesis can be accepted or rejected. Right. That finishes our second section of today's exercises, and we're now going to get a brief first look at principal component analysis, namely at techniques of reducing the dimensionality of high-dimensional data sets. High-dimensional meaning typically more than 2 data sets. We have only worked with 2 so far, and we will do that for demonstration. But we'll do that in a second. So what we can start to do with, we want to understand how does PCA work, and simply put, PCA is a technology, like many others, is the basic technology to group together all those data sets that are strongly correlated. So those where there are strong correlations, they will be put together and assumed to be a single data set, so to speak. Right? Ideally, if they were exactly the same, you would say, I don't need multiple copies of the same data set. I don't need multiple copies of the same data set, but I would just consider one and see which of these data sets are the ones that look alike and separate them from the others. So to do this, I start here. Thank you for preparing this already. If we start with a data set like we did before, and we're going to look at a correlated data set. So I introduce some correlation, assuming, for example, here in this data set that has variance 1 in both data, and the covariance or the correlation would be 0.9, so comparatively strong correlation. And to get an idea of what this data set looks like, we do what we did before, namely do a scatter plot of those 2 components against each other. So that would be all the data points of the first data set against all the data points of the second data set. And if we make a scatter plot of this, we can see, yes, we have, how many samples did we do? We have 10,000 samples. We have a nicely correlated data set with scatter plot aligned along the main diagonal in this plot here. They are generated from a normally distributed set, so we have both negative and positive numbers in this cigar shape. Right, so this is our correlated data set. Now, what we're going to do, we want to get some means of knowing how to group these 2 together. So we do this by using principal component analysis. Print-comp is the functionality in MATLAB, and it's applied in a fashion like this. We make a comment here, principal components analysis, principal component analysis. We apply print-comp, the function print-comp, on our 2 data sets M. Now, the important thing here is to know that the output of this is somewhat rich. There's actually three things that you get out of it. So, first thing that you get out is the so-called eigenvectors. We have talked about it in the last session in detail, so you might want to look it up in the first session of this module too if you are unsure. The eigenvectors will be collected in the first output of this printcom functionality.
So those are the directions we're interested in.
They will give us some hint of the direction in which to work with the data. I'll come to this in a second. Second thing is what they call the scores. They are actually already the manipulated data. So the data collected into the principal components along the directionalities given by the eigenvectors. The first output, we get the scores, we get the transformed data. So that's a transformed data set along scores. And the third output is the so-called eigenvalues to give us a sense which are the most important components of the eigenvectors. So we can call these, for example, eval, for short for eigenvalues. But we're not really going to need them now. But they are important because they help us to order the eigenvectors such that the most important one comes first. That's an inbuilt feature of the printcom function, so we can make use of this when we want to plot this. So we put this into figure 1, which is our data set. We want to keep the old plot. We want to see our data, so I put hold on here. And now we want to have the eigenvectors plotted. We want to see what are the directions of strongest correlations. And you've seen that the eigenvectors show us the strongest directions, the direction of strongest correlations. So we can plot the eigenvectors. Here. Now, what are the eigenvectors? The eigenvectors, we want them to start at 0, and we want to see the first eigenvector, the strongest eigenvector, that's principal component number 1. And we get its first component in the x direction, and we get its second component. I need to put this into an array.
So they need to be an array. So that's
they need to be into an array.
So there's the x start and the x end.
That's the start and end. So we want to start from 0, go to the first component of the strongest eigenvector, and then we do a similar array. We go from 0 to the PC second component of the first eigenvector.
So we're just drawing a line there where we're given the plot command the start and end components of the x-axis and the start and end component of the y-axis.
Right. So if I just plot this, and if I assign it a color like red, take this away, then this should now be possible to plot the strongest eigenvector. I would need to get into the first figure. No, not yet there. We have done something wrong. We have not defined PC.
But you haven't run the...
We need to run, of course. We need to run them all together. First, we need to get them, the eigenvectors, and then we can plot them. So we do this. Now we have an error here. There's something wrong. We can't have that called PCA, I think.
We call it PCA script. So you think that's because there's already a command called PCA in MATLAB?
Because there's something called PCA, which we save.
Oops, sorry.
This is what we want.
So because MATLAB already knows there's something called PCA, it's complaining when we try and call our new script that we've called PCA because it thinks it's a function. So we've just renamed this file to PCA script, and this should hopefully run.
Giving it a different name.
Yes.
And now we have the eigenvector component plotted, and I make it more obvious by making it much thicker. So you can see in the plot that the first eigenvector, if plotted into this graph in the data, is exactly aligned along the direction of strongest correlation. So it shows us that the first component basically picks up these two time series as very strongly correlated. We can also plot the second eigenvector, which would be a very similar command. So maybe I'll put that on T, plot eigenvectors. And that would be now the second eigenvector. And the second eigenvector, and maybe I give it a different color. So it's also there now, but I have left it to a thin line. It's orthogonal to the first vector, means it picks up all the rest. So there's only two time series, so we have only two. So the first one picks up the strong correlation, and the other one is orthogonal to it. It takes up all the rest. We can see there's still some variability because correlation is not perfect. So what can we do with this information? Now we know where is the principal direction of correlation. Well, we can use it to rotate. We can use this to rotate it such that we get only one component out of these two time series, that the strongest eigenvector is no longer along the diagonal, but is actually horizontal.
So you're saying that effectively we look like we've got a new axis here. So we want to rotate the rest of the data to follow that new axis if that was our original x and y axis.
Right, exactly. What we want to have is we want to have the axis going along this strongest direction, so going diagonally, or we want to have the data set rotated such that it falls only on the horizontal axis. And that would mean putting the strongest covariance, the strongest variation, on one of the axes rather than having two axes, and that would be our reduction in dimensionality. So here we have two axes that we need to display this, but we would like to do this with only one because they are strongly correlated. So how do we do that? We make a new figure, and I give it a comment. What we now plot the first principal component. We know there's only one here, it's only two data sets. So the first principal component, what will it look like? So we take those directions given by the eigenvector and we put all the original data along this direction. So we make it our new axis. And we know where these are. They are already in the output of the princom function, namely they are called the scores. So all we need to do is now a scatter plot of scores.
So that princom function also did the rotation for us as well.
The princom did the rotation already and outputted the new data, the transformed data, into scores. So what we are going to do now, we take our new data. The first data set is scores, all rows in column 1. And likewise, the second data set will be all rows in column 2. So if we make a scatter plot of this new rotated data set,
it's because so it
that
like
is something that looks strange, but we'll have that corrected soon. It looks like it's not cigar shaped, but it's like round. Why? Because MATLAB assigned it automatic axis. So we assume that the x-axis is okay if it's -6 to 6, but let's also adjust it and make it a square plot. Namely, make also the y-axis go from 6 to 6, and then we can see, yes, it did it. So now we have all the correlated data on a single axis, namely on the horizontal axis. That is our dimensionality reduction. We have collected the two data sets and put them into one horizontal axis, which is called the principal component. And the nice thing is that, of course, here we can do it by hand. It's easy to do. Also, we can just directly rotate it. But if you have 10,000 time series, you don't want to do it by hand. So the eigenvectors, if they are organized according to the strength of the eigenvalues, and you know what are the strongest ones, then you can do this dimensionality reduction from any sized matrix. And you can catch the strongest correlation and put them into what we now call the principal components, into a reduced data set.
So you're saying, in some way, if we had, so we've got only two variables for each data point, so x and y in the original plot. So here, can't find the original plot. We've lost it. So we had X and Y in the original plot, so X long, X is Y long. We could have had Z, we could have had multi-dimensional data, we could have had many, many different variables for each data point. And what this score variable gives us is an easy way just to plot the first and second component of the first and second principal components as an X and a Y axis. Because they may be buried somewhere in the data. There may be combinations of different...
There may be combinations of data that you don't know. So that's the thing, right? If you have 2 data sets, you can just see it directly. That's why we understand what's happening here. But if we have 100 or 500 data sets, we can't just look through all of them manually and find all those. Well, we could, but it would take a long, long time. And using the eigenvectors and the eigenvalues conjunctively together, we can actually get the strongest correlated data sets out as principal components.
So your many-dimensional data you can plot as 2 dimensions, as long as you're willing just to take the most important dimensions in that data.
The 2 most important components, right? You can use as many as you like. Of course, there will be as many principal components as there are data. So you will have the same number, but you know which ones to discard. So it's a way of, you could put it that it's a filter that separates noise from generic correlations. So it puts the noisy parts, or those parts that can be considered noise, into all the smaller principal components, and it takes the strong correlations, the non-noisy parts, hopefully the genuine correlations, into the first principal components. So that's why we only look at the first.
Allows you to show the most, in a sense, the most important parts of your data.
Hopefully the most important part. Of course, it's not very easy because there might not be 2 strongly correlated data sets among 500 non-correlated data sets. Typically, you have a very much more mixed view, like in the ovarian cancer data set that is used in the materials for this session, but this is the way that it works. So we have an automatic way, and we should also mention that this comes under many different disguises. It's not always called principal component analysis. You can find it under singular value decomposition. There are other names that go to it with certain variations, and some people also prefer not to use the eigenvectors directly, because they form an orthonormal basis. They're always in the Euclidean space, they're always 90 degrees with respect to each other, but sort of find the best vectors, the empirical vectors, and then it calls Cahunen-Loewe transformation, and there's many other names, empirical decomposition. But they all have the same idea, collecting the correlated ones into single principal components.
I think the most important thing is if you see something called PCA, principal component analysis, or SVD, which is single value decomposition.
Singular value decomposition.
Or something similar, or if you follow a reference and it tells you about, it comes to one of those terms, then effectively that's what the author of the paper or the author of that particular bit of research is doing, is something like this.
Right, and there's an important warning that goes with this. If you apply any of these techniques, there's a number of different MATLAB functionalities to also do SVD, would be the singular value decomposition. But if you apply them, you actually have to very carefully read the description of this function, what it outputs you and how this is done, to make sure that you actually get what you want and not there's some confusion, because the convention is not the same in these different functions. That's a confusing thing, and you have to make sure that you read the help, because you will otherwise not be able to interpret your results. Right, we're getting to the end of our session. Let me clear this a little bit. So if you have followed us, you have some code that allows you to do these calculations. We might just use the last minutes to do a very simple thing and to have a look at something that has caused a lot of problems for many of you in previous cohorts, namely the covariance matrix of the ovarian cancer data set. So if we follow I think it's this ovarian cancer. If you load this data set with the function that you also find in the materials, we can easily calculate the covariance matrix covariance matrix of this data set. And of course, we know that the covariance matrix is something like using the cofunctionality, and then we need to know what are our data. Our data are, I think I just clear this whole space and do it again. So our data are collected in something called OPS. There's a thing called OPS. These are our data. It's too long to go through. It's 4,000 times 216 times 4,000 data set. And if you have looked into it, from 216 patients or control subjects, they measured 4,000 biomarkers from a blood serum sample. So this is where we want to have the covariance matrix from. But because now we don't have time as our independent variable, but we have patients and markers, we need to know in which way this thing OPS needs to be evaluated to get the covariance of the right thing. So if I just apply this thing to the data as they come, as is called OPS, so I should actually do this. Let's just wait for it to end and we'll get...
So it's calculating something very large.
It's doing a very large calculation. Sorry, I'll just have to interrupt this. Do it again, and we get our covariance matrix, which we can immediately look at. And we can look at the covariance matrix by using ImageSC. And if we do the covm...
So ImageSC is a function that converts individual numbers into a picture. So a matrix of numbers into a picture.
Yeah, we want to have a picture of this covariance matrix. And if we do this, we get a picture, but it's all blue. And the way to debug this is not the correct picture, as you can see from the material. The way to debug this is to just look along the axis. What is along the axis? You can see this is a 4,000 by 4,000 matrix. And if in addition you put in the color bar, you can see that these values by the type of blue are all near zero. So you have 4,000 by 4,000 matrix, and it's all near zero, so that's obviously not wrong. What you have calculated is the covariance between the patients. But obviously what you want is you want for your 216 patients, you want to have their markers compared against the markers of the other control or patient. And this needs to be done by flipping the matrix around and using this apostrophe here to flip the matrix around and to make it in the right way. And if you do this, you will get the right picture for further manipulation. So with this frequently asked question, I think we stop our session now. Bring back our camera. And we have successfully ended our exercises. We'll put up a video of the session on the web page. And if you download the PDFs, you can also have the worked out code, the one that we produced here. You can have it for further reference later.